All right, welcome back. We are now going to talk about primal dual and its application to shortest path. In the previous lecture, we saw what shortest path was. The two lectures prior to that, we saw what primal dual is doing. So let's start out by writing the primal and also writing its dual. So the primal for shortest path, we have a cost vector C, C transpose F, subject to my flow conservation constraints. AF is equal to 1, 0, 0, 0, 0. And note that I have eliminated the row corresponding to node T, my terminal node in my shortest path. I'm looking for shortest path from S to T. And that's simply because I can eliminate any one of the rows from the flow conservation, because to eliminate the redundancy, and I'm just choosing that one in this case. And F is non-negative. So this is nice for us. We have a problem in standard or canonical form. This is the primal. And the dual is asking us to maximize P transpose B. Well, B is the vector with zeros everywhere except for 1 on the S value. So this is just PS. Subject to P transpose A less than or equal to C. What does P transpose A look like? Remember that A, every column of A corresponds to an edge. And it has a +1 where the edge originates and a -1 where the edge terminates. And that's it. So P transpose a column of A is just going to equal Pi minus Pj. So it has a particularly nice format. Less than or equal to Cij, and this is true for every edge ij. I also have to ask for Pt to equal 0. This is for that row that I eliminated. And other than that, P is free. So what is the basis of primal dual? It's always, let's start with a dual solution. It could be anything. I'm not even asking for it to be an extreme point. I just start with a dual feasible point. I shouldn't say the word solution. It's not a solution to the problem. It's not the optimal value. I'm just taking a dual feasible point. And and then I look at which of the inequality constraints are tight. That's my set of admissible variables. Those are the only, in the restricted primal, because I want to satisfy complementary slackness, those are the only variables on the primal that are allowed to be non-zero. So in this case, the admissible columns, which in this case corresponds to admissible arcs for a dual feasible point P, is using the same notation we've used in the past, J, which is going to be some subset of the edges, where Pi minus Pj is not less than Cij, but exactly equal to Cij. So this is where we're starting from. So now we've got the primal, we have the dual, we know what J is. Let's write the restricted primal and the restricted dual. So the restricted primal, I'm going to minimize, as usual, the sum of all of my auxiliary variables, subject to AF plus XA is equal to that same right-hand side vector. Note that the right-hand side vector, as we had assumed in our original framework, can be made non-negative without loss of generality. Here it was naturally non-negative. If I had a +1 and a -1, I would have had to flip the signs of that row in A, but I can always accomplish it. Fij is greater than or equal to 0. This holds for every ij. But also, Fij has to equal 0 if ij is not in capital J. This is the restriction. This comes from complementary slackness. And also my auxiliary variables are non-negative. Okay, so now let's write the dual restricted primal. Maximize PS subject to PI minus PJ is less than 0. Remember, I had a cost there. That has gone away. That's the combinatorialization of the cost. And so this is true only for all admissible columns. For every ij in J, the tight constraints from the previous, from the dual solution where I started. Then I have my PI less than 1. That comes from the identity matrix that's sitting there. And otherwise, well, PT is equal to 0, and otherwise P is free. And so this is my dual restricted problem. So let's write that down again. Just max PS subject to PI minus PJ less than 0 for every ij in J. And PI is less than 1, and PT is equal to 0. So this problem is something that's now very easy to solve. It's essentially, as the title of the slide suggests, it's a reachability problem, and we can just essentially look at it and see what the solution is. So the solution, P bar, again, so how can we see that? Well, PI, all PIs have to be less than 1. So I want to maximize, so I want to make PS equal 1. And if I make PS equal 1, right, so this is my graph here. If I make PS equal to 1, then I better make this edge equal to 1 as well if there's an edge in J, if this edge is in J. And so on. So basically, but on the other hand, I'm going to have a problem because this is T here. This is set to 0. If this is set to 0, then anything that backwards connects to T, anything that can get to T, better be 0. So here we're going to have a conflict. Let me write out what the solution is, and I think you'll see what I'm explaining. So the solution P bar is equal to. Let me move this a little bit out of the way here. P bar is equal to 1 for every I that's reachable from S, but from S using arcs in J, because it's these constraints that force this propagation of the 1 from S, and similarly it's those constraints that force the backward propagation of 0 from T. Using arcs in J, it's 0 for every I from which T is reachable, again using arcs in J. And then we can just put a 1 for all other nodes. All other nodes. Okay, so P bar is easier to compute. It's not difficult. Note here that I did not use the simplex algorithm. So we need to potentially make a different argument for finiteness. I did not use the simplex algorithm. But let's leave that aside from now. We're going to revisit that, especially when we talk about max flow. And theta also is easier to compute. So theta, the formula is min over all arcs ij that are in J complement, such that Pi bar minus Pj bar is strictly greater than 0. Again, ij only in J complement because Pi bar minus Pj bar is less than or equal to 0 for every J, for everything that's in J. And note that if it's strictly greater than 0, just because of the constraints here, it will be 1. So that means that the expression that I typically have, Cij minus pi minus pj, no bars on the pi's here. This is of the dual solution that seeded this whole thing. Usually I have a denominator. My denominator is usually p bar transpose aj, but that's going to be 1 if it's different from 0. So I can just omit that. So again, it's more simple. And what happens? Well, as we mentioned, the winning ij, the argument, now becomes tight. So the arg min, let's call that I hat, j hat, that's a new edge. It becomes tight in the constraint pi hat minus pj hat equals ci hat j hat. So it becomes tight for p new, which is equal to p plus theta p bar. That means that we now get to use that edge in the new reachability problem. So as a kind of just a foreshadowing of what we're going to see, I'm going to work out a specific example. If we started with p to be the all zero solution, that means that none of the edges are tight. And that means that I can set 1 to all of these values in p bar. But then what we're going to see is going to happen is that we're slowly going to add edges. And as we add edges, we'll eventually get to the situation where there is a path from S to T. And what happens as soon as there is a path from S to T? So let me take this a little bit slower. So we have the argument I hat j hat becomes tight. So we have a new edge in the reachability problem, which is the solution to the dual restricted primal. And what happens as soon as there is a path using edges from J from S to T? So what happens? Look at the solution. Look at P bar here. As soon as that happens, note that S becomes reachable from T. But if T is reachable from S. S is a node from which T is reachable using arcs in J. If that happens, the solution here for P bar has to set PS equal to 0. If PS is equal to 0, the solution to the DRP is equal to 0. By strong duality, that means that the solution to the restricted primal is equal to 0. Let's remind ourselves what the restricted primal is. The only way for the restricted primal to have an optimal solution of value 0 is if it's not using any of the auxiliary variables, which means that we have a solution using only the original variables f that satisfies complementary slackness, and hence we're optimal. That's the story here. So let's see an example that's a little bit more interesting than this one with 4 nodes, just to see the steps. It will help us again, help us embed in our minds the process of this primal dual, and it's also going to help us see it in action and seeing how it has a combinatorial interpretation of what this primal dual algorithm is doing in each iteration. Okay, so let me explain what we've got here. This is a graph that describes a shortest path problem. It has 8 edges and it has 6 nodes. I've drawn in the directionality. I've labeled the edges. So there's a lot of labeling going on because I need to label the edges. I've used E1 through E8 for that. I need to label the nodes. But then I need to label the costs. That's what I've circled. So the value 2 is the cost of E1. The value 5 is the cost of edge 8. But I'm going to have to do more than that because the dual solution assigns values to the nodes. So I'm going to have to label something that's going to compete with the numbering. So I hope it's clear. I'm kind of keeping the, I hope it's clear. Okay, so here is my problem. And just like I suggested on the previous slide, if you look at the dual, we initialize the whole primal dual approach by just picking a feasible solution. Since the costs of the edges are non-negative, you don't get paid for choosing an edge in this case. P equals 0 is a dual feasible point. So let's initialize there. Okay, so let's see what happens. Here's my picture again. So note again here that here are my labels. This is node S. I've labeled this as 1, 2, 3, 4, and T. So I have 6 nodes, S and T, and then 1, 2, 3, 4. And then closer to the node, again, sorry for this is complicated, just to hope it's not too confusing. I've written the dual solution. So P is equal to 0, 0, 0, 0, 0, 0. That is also reflected in this drawing. Okay, so what's J? J is a set of edges for which Pi minus Pj is equal to Cij. But Cij is always positive. There's no zero cost edges, and Pi and P's are all 0. So there's nothing in J initially. No admissible edges. The restricted primal is very simple in this case, because basically everything has to be 0. What is the dual to the restricted problem? I'm just flipping back just to see it once. I won't do this all the time. The dual to the restricted problem, it asks me, in addition to P less than 1, I need Pi minus Pj to be less than 0, but only for every ij in J. So if J is empty, then this just goes away completely. So all I have is Pi less than 1, and you can see just from that of course, I've suppressed I should have written out the constraint Pt is equal to 0. This is always there. So I've got, I have got that my P is, P bar is 1, 1, 1, 1, 1, 0. I need to move this slightly because you are, oops, shucks. I may not be able to fix that. Yeah. Well, too bad for me. I need to move it because it is. I'm very annoyed now. It's behind the. It's behind my my image in the recording. Well, I guess I can do it differently too. Hate to do that. Okay, probably this made no difference for you on your end, but in the recording it all shows up. Okay, so now let's look at the upper right hand corner here, and what I've drawn is the value of. I drew all the j's, the edges that are admissible. There are no edges that are admissible, so there's nothing there. I drew 1, 1, 1, 1, 1. And 0. Those are the dual. That's P bar. And how do I choose theta? I look at all the cases where Pi bar minus Pj bar is strictly greater than 0. For all the edges that are missing. And in that case, where is Pi minus Pj with bars strictly positive? For none of these edges, because everything is labeled 0. All the P bars are 0 here. The only positive, all the P's are the same with the exception of the P bar that corresponds to T. So the only instance where Pi bar minus Pj bar is greater than 0 is when J is equal to S. So I have 2 edges here that are candidates that are in this minimization. And I want to minimize over these 2 edges Cij minus the original pi minus pj, which is 0. So I'm minimizing cij. So I'm choosing over 2 and 5. Only these edges are in play. 2 is less, so I add that 2, and theta is going to be equal to 2. What's going to happen in the next iteration? The next iteration, I'm going to update. I have to move around this thing again. Now I've added an edge to j. Edge 7 is in j. And so I've added this edge. What is my new dual solution? It was what I started with before, 0, 0, 0, 0, 0, 0, plus, that's my p old, plus theta, which we found is 2, times p bar, which was 1, 1, 1, 1, 1, 0. Add that, I get 2, 2, 2, 2. I've lost track. Anyway, I get that. And we've added this edge here. It's easy to come up with p bar. It's just a reachability problem. I get to assign 1 to s and 1 to everything, 1 to these 4, but I have to assign 0 to the third node. That is this 0 here. Why? Because it's connected to t. Apologies, there's a 0 here missing for p bar because that corresponds to t. It's connected to t. So I have to put a 0 from all nodes from which t is reachable, and that is this node. And therefore that's my next p bar. Similarly, I can compute theta. Theta equals 2. Choosing theta equals 2 makes another one of my constraints tight. That constraint corresponds to the 6th edge, which is the one that's dotted. And we continue on in that way. The next p I obtain in the same way. P old, which was 2, 2, 2, 2, 2, 2, 0, plus theta, which is 2, times the p bar that I computed. Now I've added 2. I have 2 tight edges. Again, I solve my reachability problem. Anything, in order to get p bar, anything which can reach t has to be assigned a 0 because pt is equal to 0. So this node has to get a 0, and this node has to get a 0, but everything else can get a 1. That's my p bar. I compute my theta in the same way. In this case, I make 2 constraints tight. Both of these, E4, these correspond to E4 and E5. That means that E4 and E5 are added to my constraints. Are added to J, and the reachability problem continues. And in the last step, I add E2, and once I add E2, I have to choose P bar equal to all zeros, because from any node, you can reach node T using only edges in J. And therefore that 0 is propagated back. P bar equals 0, which means that the optimal value to the dual restricted primal is PS, which is equal to 0, which means by strong duality that the restricted primal has optimal value 0, which means that we satisfy complementary slackness. So this is the story here, and we went over it somewhat quickly, but you should go over it again. And just a brief discussion here, wrapping up. If at any time in the iteration you look at the set of nodes from which T is reachable from I using arcs in J, this is what we kept doing over and over again. Right? This is the I such that Pi bar is equal to 0. And you can see that basically this means that Pi in the optimal solution, when I update, P new is equal to P old plus theta times P bar. That means that Pi remains fixed because I'm always going to have zeros in P bar once I can reach J. So Pi remains fixed once I is in W. And you can show with a little bit of thought here that as soon as I is in W, the value pi is in fact equal to, the dual variable encodes the solution. It is the value of the, or length of the shortest path from I to T. And essentially in here, you can see that this is related to Dijkstra's algorithm for shortest path. We're finding all of the shortest paths. When you solve a shortest path problem, you find the shortest path from every node to T. We're going to stop here, and next time we're going to talk about how to combinatorialize the right-hand side, which involves a new idea by looking at the max flow problem.